In the last lecture, we began with extending our simple two-variable regression model to a multiple regression model. So as an example of a multiple regression model, we took the simplest possible case, which is a three-variable model. Our three variables are y, which is the dependent variable, and two independent variables x2 and x3. So we discussed the formulas of the estimators. We had a look at the variances and the standard errors of the estimators. We also discussed two additional assumptions to the CLRM, which are required when you have more than one explanatory variable. Right? Now let's have a look at the properties of the OLS estimators. The first property, similar to the numerical property that we discussed in the two variable case, is that the three variable regression function also passes through the mean values of y, x2 and x3. This is evident from the first normal equation if you look into the slides that were shown in the last video. Now this property can be extended or generalized for a k-variable regression model. So a k-variable regression model will be specified as yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i, etc., plus beta k ki plus the error term ui. So when you have a generalized k-variable regression model such as this, the first normal equation of that model will give us the formula for the beta 1. Remember, beta 1 in all these models represents the intercept term. So beta 1 hat will be y bar minus beta 2 times x2 bar minus beta 3 times x3 bar. Remember, I'm sorry, this won't be a hat, this will be bar, minus etc. beta k x k bar, where any x bar means the particular variable's mean value from the sample. So x2 bar means the mean sample value of x2, x3 bar means the mean sample value of variable x3, and so on. The second property is that the mean value of the estimated yi values, which in other words is the yi hat, so the mean value of yi hat will be equal to the mean value of the actual observed yi. This is also a property that we discussed in the two variable regression model, and the proof is along the same lines as the two variable regression model. If you want, I can show it to you in this way. So remember that we are saying yi hat, that is the estimated yi, will be beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i. Now from the first property we know that beta 1's formula can be expressed as y bar minus beta 2 hat x2 bar minus beta 3 hat x3 bar, and the remaining equation remains as it is, beta plus beta 2 hat x2i plus beta 3 hat x3i. So now I can write this as y bar plus, I'm taking beta 2 hat common, so I'll get x2i minus x2 bar. That means deviation of each x2 variable from the mean. When I take beta 3 hat common, in the bracket I will have x3i minus x3 bar. So this is equal to, remember this is equal to, so I can actually write this as yi hat equals to y bar minus beta 2 hat small x2i plus, sorry, this is plus beta 3 hat small x3i. Remember, throughout these lectures, small letter x and small letter y all represent deviation of the variable from the mean. Now, to prove that the mean value of yi hat is equal to the mean value mean value of the observed yi, I can sum up the equation on both sides. So when I sum it up, I'll get summation yi hat is equal to, since y bar is a constant, if I sum it up over n times, because n is the sample size, I'll get n times y bar plus beta 2 hat summation x2i plus beta 3 hat summation x3i. Now one second, I'm just trying to get another, I don't know why I can't get it. Okay, fine. Now summation x3i and summation x2i is the sum of deviations from mean, and deviations from a central value such as the mean, the sum of such deviations always equals to 0. If you remember, in the when I was discussing the 2-variable model, I had shown it to you using an Excel sheet, right? So summation of deviations from a mean value, central mean value, will always be equal to 0, which means my second two terms on the last two terms on the right hand side of the equation become equal to 0. So I have got summation yi hat is equal to n times y bar. Now if I want to find the mean of yi hat, I need to divide the sum of yi hat by n. So if I do that on the left hand side, I should also do that on the right hand side. So on the right hand side, n and n cancel, and what I have got is, this implies yi hat's mean value is equal to the mean value y bar, which is the mean value of actual observed y's, right? So this is the logic of this proof is exactly the same as I did in the 2-variable regression model. Once again, I don't think the proof will be asked, but I showed it to you so that you're very thorough with the concept. Okay, now while I'm discussing this, let me also tell you that the regression equation yi equals to yi hat equals to beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i. Since it can be represented as this. I can write from here, I can actually write this relation, that is yi hat minus y bar is equal to beta 2 hat x2i plus beta 3 hat x3i. So yi hat minus y bar, I can write it as small yi hat, so that again small letter yi represents deviation from mean, is equal to beta 2 hat x2i plus beta 3 hat x3i. Now based on this, I can write the regression equation in its deviation form. In its deviation form, the SRF can be represented as yi is equal to yi hat plus ui. So instead of yi hat, I'm writing it as beta 2 hat x2i plus beta 3 hat x3i plus ui. Right? This is called the deviation form, where instead of the variables capital Y, capital X2I and capital X3I, I'm writing in terms of their deviations from mean. Right? So when you write a regression equation in its deviation form, note that it does not have the intercept term. There is no beta 1 hat in this form. A similar deviation form had also been discussed or derived when we were dealing with the two variable regression model. Okay, so remember that in deviation form, when you express the regression model in deviation form, it does not have an intercept term. In some instances, the deviation form has simpler calculations involved. So estimating a regression model in the deviation form sometimes has a few advantages. The third property is that summation ui hat in the multivariable model is equal to 0, which also means that the mean of the error term is equal to 0. This can be easily verified if you look at the earlier deviation form equation. This can be easily verified. Once again, I'm not discussing the proof because we covered similar proofs in the two variable model. The fourth property is that the residuals, that is the terms ui, are uncorrelated with all explanatory variables x2i, x3i, and if it is a k variable regression model, then up to xki. To show that they are uncorrelated, we can show that summation ui hat x2i and summation of ui hat x3i are all equal to 0. Remember, these properties we are specifying for a 3 variable regression model, but these can be generalized to a k variable regression. Similarly, the fifth property is that the residuals ui hats are uncorrelated with yi hat. Intuitively, again, now that we have discussed so much, we can say intuitively that we know that ui is the residual term that captures all the remaining influences on y which are not systematic. which are very random in nature. So it automatically means that the yi hat and the error terms ui hats are uncorrelated. Because if they were correlated, that means there is some sort of systematic influence on yi hat from the variables that are all encompassed or that are all collectively held in the error term, right? So as long as we have the assumption that the model is correctly specified, all those variables that systematically influence yi have been included in the model explicitly. It is only all the remaining unimportant variables whose influences are summed up together in the residual term. So as long as our model is specified correctly, my error term will not be correlated or will be uncorrelated with yi hat. The sixth property is something slightly new. It states that as the correlation coefficient R23, this is the correlation coefficient between the two variables, independent variables x2 and x3. As the correlation coefficient approaches closer and closer to 1, the variances of beta 2 hat as well as beta 3 hat will increase towards infinity, right? If you're confused about this, you just have a look at the formula for variance of beta 2 and beta 3 that I had shown in the slides in the earlier video. You can see that the R23, the correlation coefficient term, appears in the denominator of the variance measure. So if the value in the denominator increases or approaches closer to 1, you can see from the formula that the denominator is becoming equal to 0 or approaching 0, and therefore the variance of beta 2 hat as well as beta 3 hat is approaching infinity. Now remember, we are concerned with variances of these estimators because we say that the reliability of the estimator is measured by the standard error. Standard error is nothing but square root of the variance. So if your variance is approaching infinity, that means standard error or the square root of it will also be very large, which means the reliability of the estimator that we are talking about will be very, 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 very less. So closer the correlation between the independent variables x2 and x3, the more difficult it will be to know about the true values of beta 2 and beta 3. Simply because the estimators beta 2 hat and beta 3 hat are not reliable. They have very large standard errors. Once again, if you have a look at the formula of the variance for beta 2, you can see that given a value R23, that is correlation coefficient between x2 and x3, and summation x2i square as well as summation x3i square, given these values, the variances of the OLS estimators beta 2 and beta 3 will vary or will be directly proportional to sigma square. Sigma square is the population variance of the error term. okay, since the formulas were written in the, let me just write the formula here in ink. So I'm saying that variance of beta 2 hat, I'm writing the simpler formulas which use the correlation coefficient. For beta 2 hat, it is summation x2i whole square into 1 minus r, r23 whole square, right? This is my variance of beta 2 hat, and variance of beta 3 hat is equal to sigma square divided by summation x3i whole square into 1 minus r 23 whole square. So if you just look at this, you will get the above answers. For given values of r23 and summation x3i whole square, x2i whole square, the variance of beta 2 hat will be inversely proportional given the value of r23 and sigma square, the variance of beta 2 hat will be inversely proportional to summation x2i whole square. Similarly, we can talk about variance of beta 3 hat as well. For given sigma square and r23, the variance of beta 3 will be inversely proportional to the summation of x3i whole square. Again, this is directly evident from the formula, because summation x2i square comes in the denominator of the variance formula. Similarly, summation x3i square is also in the denominator of the variance of beta 3 hat, right? And once again, smaller the variance, smaller will be the standard error, which means more precisely we are able to estimate the true population beta 2 or the true population beta 3. Finally, given all the CLRM assumptions, these OLS estimators, whether we are talking about a 2-variable model, a 3-variable model, or a generalized k-variable regression model, all the estimators, OLS estimators in such a model will be blue, that is, they'll be linear, unbiased, and they will have the minimum variance among the entire class of linear unbiased estimators, which is they are the best estimators, right? So that's it for now. I'll come back with a follow-up video where we shall look into the multiple coefficient of determination r square, that is capital R square.